So let's refresh our memories on what a function is. We're not going to go through the technical textbook definition. No, y is a function of x if and only if for every single x there exists a unique. That's just too complicated. Let's just go ahead and do the informal or layman's terms definition. So what is the informal idea of a function? I hate to use a cliche, cliches are sort of not clever, but I will use one here because it's a good analogy. A function is an input, output machine, right? So that you can sort of think of a function as a machine. You put something in it, and it gives you something out. Now, since we're talking about math, it's usually going to be numbers. You put in a number, and then it's going to spit out a number. But what's so important about this machine is it has to, quote, work. A function is an input-output machine that always gives you the same output for the same input. Again, to borrow a cliche metaphor, functions like a vending machine. We would say a vending machine works if I press B7 one day and it gives me a bag of Doritos. The very next day, if I hit B7 again, it should give me a bag of Doritos. That's what we consider a machine that works. If suddenly, one person hits B7 and then Doritos falls out, and then the very next person behind me presses B7 and gets Cheetos out, then something's wrong with that machine. So informally, that's what a function is. It's just a machine that works. Every single input you put into it, I expect to get the same output every single time. Functions have a specific notation, not surprisingly called function notation. For example, f of x equals 3x minus 2. And the parts of the notation are pretty self-explanatory. This f here is sort of like the label, or it's the name of the function. And the stuff inside the parentheses is the input, right? So a common mistake students make is that they read that as, oh, that's f times x, which is not the case in function notation. We actually read that as f of x, which probably doesn't help any further because in math, the word of does mean multiply. But in this case, it simply means the function value at x. And every single function, since it's a machine, needs a rule. Right? So this literally says, my rule is whatever you put into it, multiply by 3, and then subtract 2 from it. When it comes to function, and the labeling, there's no special reason why we use f. I think f is common because f stands for function. But you could have g of x, you could have e of x, you could have anything. You can have smiley face of x if you want. It doesn't have to be x's. You could have g of y, although that's sort of confusing. You could have s of t. So function notation, when you lead it off, it's just a label and an input. Right? It could be numbers as well, k of 4. That's function notation. That says use the k function and my input is 4. Everything that you input, the pool of things of our inputs, we call that the domain. So this is just more vocab. So by definition, the domain is the set of all viable inputs. And again, before I said, your inputs could be any variable. Typically, if it's not a word problem, if it's not a context, our inputs we usually use as x. And the twin definition, or the twin vocab word of domain, is range. This is the set of all outputs. And again, if you have a word problem, your output might be whatever. It might be C for cost. It might be V for volume. But in general, the outputs are usually your Y values. Now, function notation is sort of a command. It tells you to do stuff. It tells you to evaluate. So if I asked you to do something like this, for f of x equals, I don't know, 3x squared plus x minus 5, evaluate letter A, f of 2, letter B, f of negative 1, letter C, f of x plus. Pick your favorite number.
5.
5. All right, that's going to suck when we multiply it out, but sure, we're adventurous. Okay. Now remember, in function notation, all this says is whatever is inside the parentheses is your input. So I guess I should probably use different colors. All right. So whatever is inside of these parentheses, that's what you're going to substitute for the original x's. That's all function notation says. So for letter A, I'm going to just copy down this guy, 3x squared plus x minus 5. The only difference is wherever we see an x, I'm going to put a parentheses 2. So 3, I guess I should write f of 2 equals 3, instead of x, just write parentheses 2 squared, plus instead of x, write parentheses 2 minus 5. That's it. That's you evaluated. That's how we evaluate functions. And the rest is just doing math, which I'm assuming we all know how to do. So that's what? 2 squared is 4 times 3 is 12, plus 2 minus 5 is a negative 3, so plus negative 3 is a 9. All right. Now, you don't have to do this on the practice, but let's make sure we understand what happened here. We physically plugged in a 2 and got out a 9. So this function makes a relation. So all of this work implies that the input of 2 relates to a 9. So when you evaluate functions, you're actually making coordinates. You're actually making points. You actually don't have to write it out this way on the practice, but I'm just extra Jeopardy fact for you. Letter B, just do the same thing. If you saw f of negative 1, it says plug a negative 1 in for all the x's in the f function. So this is 3 times the quantity negative 1 squared plus negative 1 minus 5. So then just do math. Negative 1 squared is a positive 1 times 3 is a 3. Negative 1 minus 5 is a negative 6. So 3 plus negative 6 is a negative 3. Now, you don't have to just input numbers. As you can see, letter C, you can input other variables. I use x plus 5. It could have been a plus 5. It could have been smiley face plus 5. It really doesn't matter. All function notation tells you to do is wherever you see the original x, this is the stuff you're plugging in. So in my original function, everything that I've highlighted in pink here is going to be changing into x plus 5. So we have 3, instead of x, I'm going to put parentheses x plus 5, because that's what function notation tells me to do, squared, plus, instead of writing a regular x, I'm going to write x plus 5 minus 5. And then you just go ahead and do math. Okay. I'm actually going to do this in 2 steps. Let's expand the x plus 5 squared. So that's x squared plus 10x plus 25. Plus, and then here, the plus 5 and the minus 5, they cancel out. So it's just plus x. Distributing the 3, 3x squared plus 30x plus 75 plus x. And then combining like terms gives you 3x squared plus 31x is plus 75. Right, so that it's typical. That's our answer. Our answer has variables in it, which sort of makes sense. If I input variables, unless things cancel out, I expect to get output variables as well. Easy peasy? Right. So this example is an example of evaluating a pretty simple function. It was a polynomial function, right? Whatever I tell you to plug into it, boom, you just plug into the equation. But when you get into higher level mathematics, pre-calculus and beyond, functions aren't always nice. As a matter of fact, functions, the situations that you encounter in higher level mathematics usually will not be able to be described in one equation. You might need multiple equations. For example here, now I pulled this example straight from online, so it's a very, very old example. You guys can tell by the context of the story. Okay. So suppose a cell phone company or a cell phone plan charges $39 a month. Like I said, this is a very, very old example. I wish my plan was $39 a month. Here's how you can tell the plan is dated. The plan offers 2 gigabytes of data and charges an extra 15 per extra gigabyte. Right. The monthly charge, or charges, plural, of this plan is given by the following function. Right. So in this example, we're fortunate we don't have to come up with the equation, they give it to us. Notice they did not choose to use f of x, they chose to use c of x, c for cost, that makes sense. So c of x equals, curly bracket, 39. If 0 is less than or equal to x, which is less than or equal to 2, and then 39 plus 15 times the quantity x minus 2, if x is greater than 2. Where x is the number of extra gigabytes used. So typically in higher math, you see lots of functions being defined with this curly brackets and multiple pieces. These are called piecewise functions. And the way you evaluate piecewise functions is you can't just stick your input anywhere you want. You have to look at the domain splits here. So these domain splits in the piecewise functions are sort of like your gatekeepers. They are traffic controls. They control where you can plug stuff in. So the actual question in this example that I found was find C of 0.5, C of 2, and C of 4. Right, since I'm writing large, there's going to be a lot of scrolling back and forth, but hopefully it's all in front of your pages here. So if I wanted to answer this question, I have this very weird looking piecewise function here, and I want to do C of 0.5. I hope everyone can agree that my input here is 0.5. That's what the notation says. So what I have to do is look at my domain splits right here and ask myself which row, the top row or the bottom row, does 0.5 fit in those inequalities? Hopefully everyone can agree that 0.5 fits in the top row. 0.5 is between 0 and 2. So because that's where 0.5 fits, I guess for the notes I should write it out. Since 0.5 exists within 0 less than or equal to x less than or equal to 2, we will use the top piece. That's it. That's how you evaluate piecewise functions. And then you just do the normal thing. Okay, so C of 0.5 equals, then all you got to do is plug it into the top function. Is there a place for me to plug in an x in the top function? No, it's a constant function. So guess what C of 0.5 is? 39. Just 39. If I use 0.5 of a gigabytes, according to the plan, I'll pay $39. Right. That's easy. C of 2. Let's take a look at the original function. Which one of these domain splits will C equals 2 fit into, or x equals 2 fit into? The top one. So again, evaluate into the top function, that's just 39. C of 4 equals, so if I want to evaluate a piecewise function, my input is a 4. I have to ask myself, which of these domain splits does x equals 4 fit into? The bottom one. Clearly 4 is greater than 2. So I'm going to substitute 4, the input of 4, into the bottom equation. Does everyone understand how we're evaluating this piecewise function? Just look at the domain splits. That will tell you which piece to use. So this tells us to use the bottom function. So that's 39 plus 30, which we will pay $69. Yep. I think that's right. Yeah, 4 minus 2 is 2, 30. Okay. So evaluating piecewise functions, you just have to look at where does my input fit within the domain splits. That'll tell you which piece to go. You okay with that? Evaluating functions. It literally is just substitution. More vocab when it comes to functions. I may toss this term a lot. Especially in Calc 1, you'll be finding net changes a lot because Calc 1 is all about the study of the changes within the values of a function. So by definition, the net change of a function is the difference in y values, or outputs, I'll use outputs, between two inputs. And it's usually, not always, but it depends on your point of reference, it's usually going to be your final situation minus your initial situation. For example, find the net change from 1 to 3 of f of x equals x squared. Right. So in this example, notice they give me a function and they ask me to find the net change between these two values here. So these guys here are your inputs. And this right here is your function. No duh, because it's f of x. So by definition, net change is the difference, subtraction, of your outputs, of your y values. They didn't give me my output, so I got to find it. So before I can answer this question, we got to find the outputs at 1, the outputs at 3. So what's f of 3? That's just 3 squared, which is 9. What's f of 1? That's 1 squared, which is 1. Hopefully that was not too much trouble. Net change, again, it's usually, I would say almost always, if not always, the output at the latter input, the output at the bigger input, minus the output of the smaller input. Right. So in this example, 3 is bigger than 1. So we're going to do f of 3 minus f of 1. So I would say that the net change is 8. Pretty simple stuff. Hopefully you guys remember this from Algebra 2. It's pretty generic function stuff. No questions so far? Sweet. The thing that I wanted to focus the majority of this notes on, though, is finding domains of functions. For some reason, finding domains algebraically is difficult for students. Why is it difficult? Because, hey, Mr. Vo, we have graphing calculators, we have Desmos, we can just graph the darn thing and read the domain. And that's true, right? If I wanted to find the domain and had a function, say, I don't know, I graphed something and it was a parabola, right? I can just read what the domain is. How far left does the graph go? It goes forever to the left. How far right does the graph go? It goes forever to the right. So the domain is negative infinity to positive infinity. That's pretty simple. But you know what? What if you're not around a graphing calculator? Or what if, your laptop battery's at 1% because we didn't charge it overnight as we should have, or we're watching videos during class, right? I can't graph this easily. That's why it's sort of nice to figure out domains algebraically, because sometimes doing it by hand is faster than doing it with technology. And here's the cool thing. We sort of find domains backwards. By definition, the domain is a set of all permissible x values. When I, Mr. Vo, personally find domains, I do the exact opposite. I find all the x values that are, quote, bad, all the x values that I cannot use, then I just subtract it from all real numbers. Now, what does it mean to be a, quote, bad x value? Well, this is only pre-calculus, so we're not going to go through all of the different possibilities. But generally speaking, since the first time you've done math, kindergarten, maybe preschool, hopefully between then and now, your teachers have grounded into your brain at least once these two ideas. Over the field of real numbers, that is to say, if we're only interested in real answers, you cannot take an even root of a negative number. I hope by now that's just a common math fact as, 2 plus 2 equals 4. That's just automatic. We don't need to think about it. Oh yeah, I've been taught forever that you can't take a square root of a negative number. You can't take a fourth root of a negative number over the field of reals. Now, if I was expanding it to complex, you can, but we're going to stick with reals here. So that's that's not a hard idea. That's something we've already know, right? I'll take your silence as a yes. Although that did not work out on the test. And the second idea that we should have had ground into our brains is you cannot divide by 0. There's not a lot of things I'll say you can't do in math unless it's some made-up math that you've done, right? If you wanted to solve an equation, if you want to multiply first, you can. If you want to divide first, you can. If you want to add first, you can. You just got to do it carefully. But there are a lot of things you can do in math. These 2 bullet points, though, they're usually the very rare exceptions that I'll go, no, you can never, ever do these. This is what you're going to consider when you're trying to find domains of functions, because they all have some implications. For example, let's say I ask you to find the domain of 1 over x squared minus x equals f of x. Right. So yes, I could just whip out my graphing calculator, graph him, and then read what the domain is. But let's pretend our calculator's busted. Let's pretend our laptop is dead. We have to do this by hand. Well, the first thing I do is I go through those 2 bullet points. Okay, I know in math I can't take an even root of a negative number, and I can't divide by 0. Then what I do is I analyze my rule. So I look at my rule here, and I go, there's no square roots. There's no fourth roots. There's no radicals in this problem, right? So it's impossible to do the first bullet point, so I'm safe there. The second bullet point, I can't divide by 0. Am I doing any division by a variable here? Do I have any fractions? Yes. So it is possible that we can actually do the second bullet point, which is wrong. So what I'm going to do is I'm going to write down what I don't want. What is it that we don't want? We don't divide by 0. We don't want the denominator to be 0, right? That's what we'll literally write. So I'm going to write down x squared minus x, which is the denominator. I don't want him to be 0. So then what you got to do? Solve him. Even though it's an inequality, it uses a not equals to symbol, you treat it like a regular equation. So this is a quadratic. To solve a quadratic, you use quadratic formula, completing the square, or the thing I always try first, factoring. So we can factor out an x. Although the zero product property works for equal signs, we can apply the zero product property with this inequality as well. So we get x cannot equal 0, and x minus 1 cannot equal 0. So I'm not going to circle them because they're not my final answers, but are we okay with how we got these 2 results here? So this is how you find the domain, right? We did it backwards. We didn't find the set of all permissible x values. We found the set of all x values I don't want. So if I imagine a number line, and imagine this number line, everything is shaded at the very beginning, right? So everything is all real numbers. But my math says I can't use 0 and I can't use 1. So at x equals 0, at x equals 1, it's as if I erase, I guess I can't do that with this program. It's as if I erase the shading at those areas. So everything is shaded except for those two. I erased at 0 and 1. Does that make sense? Well, guess what your domain is? It's that picture staring at you in your face. That is the domain of this function. We just have to write it in interval notation. So my domain is, we have 3 parts here, parts 1, parts 2, parts 3. The first part, it starts off at negative infinity and goes all the way to 0. It's an open parentheses, union. The middle part starts at 0 and ends at 1, open parentheses because they're both open, union, and the third part starts at 1 and goes all the way to infinity. That is the domain of that function. You guys okay with that? Okie dokie? We good?
Yes, sir.
All right. Let's see if I can't do the next 2 examples a little bit faster, since you guys are telling me you guys have the idea. Let's find the domain of g of x equals the square root of 9 minus x squared. I hope I chose this example, obviously. What's the one thing that we need to prevent? What could potentially be bad in this situation? Square root of a negative number. So do you guys agree? What we want is the stuff inside of the square root to not be negative. That's what we want, right? In math, to not be negative means to be greater than or equal to 0. This translates to non-negative. So you literally write what we want. You guys told me, oh, we want the stuff inside the radical to not be negative. We literally want 9 minus x squared, the stuff inside the radical, to be non-negative. Hey, how do I find my domain? I just solved that nonlinear inequality. And we did this in Unit 1. Hopefully we remember, well, actually, I just graded your exams. So let's go over how to solve this nonlinear inequality. To solve a nonlinear inequality, you want 0 on one side, which we have here. So then we're going to pretend that it's 9 minus x squared equals 0 and solve it however you want. Solve by factoring, solve by completing the square, yada, yada, yada. Since there's only one x value, I'm just going to solve it directly. So I'm going to add the x squared over and then take the square root. When you take a square root to solve, you get plus or minus. So then you're going to plot them on the number line, negative 3 and 3. Whether or not they're going to be open or closed will be dependent on your original inequality. Since my original inequality has that line underneath it, or equals to, we're going to fill it in. And then all you got to do is pick numbers in each regions to test. Say x equals negative 4, x equals 0 is always a favorite, x equals 4 maybe. And then you just plug it into the inequality to see if the answer is going to be positive or negative. Are we okay with that idea there? So I'm going to fast forward through the check. I'm not going to show the work because all it is just plugging it in and using your calculator if you need to. But if you were to check those yellow numbers, you're going to get a positive answer on the left, or excuse me, a negative answer on the left, a positive answer in the middle, and a negative answer on the right. So I'm going to skip the check work because we did a whole bunch of that in Unit 1, but all I would do is plug in those yellow numbers into the equation, into the inequality. Lastly, to figure out your answer, you have to read the inequality. It says greater than or equals to 0. I mean, I just told you. What type of numbers, positive or negative, are greater than 0? Positive. So looking at these 3 symbols here, your answers would be the positive regions, which is right in the middle. So there is our domain. My domain starts at negative 3, ends at 3, and they're both closed. Easy peasy?
Yeah.
So that's how you find domains algebraically. Just run through those 2 things that you think to yourself, okay, what could possibly go bad here? What do I want? Write down the thing that you want and then just solve it. Okay? That's it. That is 2.1. You guys should be an expert at evaluating functions, at finding net changes, and at finding domains by the end of the section. Should be. Should is a wonderful word in English.